Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Alright, a formal good evening and greetings to grade 12 students having a look at this tutorial video and those present with me. Okay, our topic for tonight is electrodynamics. Okay, now electrodynamics are it's a subject that falls under electricity and magnetism, the topic electricity and magnetism, and is the follow-on question after your circuit question. It's the follow-on question after that, just before you get to your photoelectric effect question, which is the last question. But of course, we need to have a look at the definition of electrodynamics. Okay, now electrodynamics, first of all, is the branch of physics it's the branch of physics that deals with the interaction between electricity which is the follow-on from electric circuits, which deals specifically with electricity, but the interaction between electricity, magnetism, and movement. Alright, now the piece of machinery that exists in real life, alright, that we as Africans need to probably start investing into a bit more often in this time, this year alone, and definitely within the last decade, is generators. Okay, now we see and we find electrodynamics present a lot in generators, whether they are alternating current, so AC generators, or direct current, which is also known as DC generators. Okay, but what we must understand is that there is a backstory. So obviously, when it comes to the magnetism part, your knowledge of Faraday's law and the right-hand rule and the left-hand rule is obviously going to be required of you to understand in direction of current. I'm not sure, but I just want to check in grade 11. Just pull up a grade 11 textbook here quickly. This is module 5. Did we teach you the left-hand rule or the right-hand rule? So just give me one moment quickly, because I cannot remember. Yes, no, we didn't teach you the left-hand rule. We taught the right-hand rule. Yes, we did. So that's awesome. Okay, I don't think we did taught the left hand. Is left hand even in here? No, left hand is not in there. Okay, leave the left hand alone. Okay, unless you're ambidextrous, then of course makes sense. Okay, but the definition of electromagnetic induction with Faraday's law, okay, which that a change in magnetic field induces an EMF in a conductor. The magnitude of the induced EMF will be directly proportional to the rate of change in the magnetic flux. So we need to obviously remember. Let's pull up a little remember here. Okay, remember, of course, the induced EMF is equal to negative N, change in the magnetic flux over the change in time. That's Faraday's law. Okay, now the definition of electromagnetic induction, of course, is that an EMF as well as an electric current are induced in a conductor that's placed in a changing magnetic field. Now this is obviously present a lot inside a motor. Alright, motors also provide that same explanation of the electrodynamic rule, right? Because there is the same thing. There's an interaction between electricity, magnetism, as well as movement. Alright, especially in car motors. Okay, motors in general. Okay, now we must bring into teaching here the right-hand rule. Which is also part of remember. Okay, the right-hand rule. All right, now the right-hand rule, which is a little less common, it's called the right-hand or Dynamo Rule. All right, Dynamo. Okay, the right-hand rule or the Dynamo Rule, which was obviously Fleming's right-hand rule. All right, so obviously you're going to hold the first 3 fingers of your right hand at right angles. All right, so in other words, your index finger, your thumb is going to point upwards. Thumb does not have an E at the end. Your thumb pointing upwards. Okay, and this is the force F. Okay, your index finger, it's going to be pointing obviously forward. Okay, now your index finger, obviously like you're holding a gun, like, you know, when you were a kid, you obviously held your hand out like in a gun form, like in a 7. All right, that is the magnetic field. All right, now the magnetic field, grade 11, symbol was B. Okay, don't know if I can fit this in here, but I'm going to give it a go. And then we've got your middle finger. So if you're holding up a gun, okay, and then if you put your middle finger out on your right hand to face in the left direction, okay, middle finger, I think I can fit it in here, middle finger, that's going to obviously point to the left, right, and this will obviously indicate the direction of the current, right, which we know is electricity, which we know is symbol I. All right, so I will see, you know, I'm just going to put on my my webcam so you all can see anyway. I am dressed appropriately, so don't worry. Okay, just see if it pops on. There we go. Okay, cool. That's it. Face reveal, if you haven't seen me. So you got your right hand. This is my right hand. I'm going to face this way. All right. So you guys are on my other screen there. That's why I'm looking up and not directly at the camera. So anyway, you got your right hand. So you got your index finger. Okay. This is the force, direction of the force. So obviously you won't just be keeping your hand like this all the time. You will obviously be turning it and whatever. So then you stick out your index finger, which will be the direction of the magnetic field, and then your middle finger is going to, which I'm pointing towards the screen here, okay, this will be the direction of the current. So your fingers will look like this. Okay, cool, like that. Okay, so that makes sense, which will be the direction of the current. So your middle finger is current, your index finger is the magnetic field, and your thumb is the force. All right, so finding out the directions of all of those. Cool. Any questions on that? So here we got an example of a plane of a coil. All right, so this plane of a coil, all right, is perpendicular. This is the sign for not perpendicular, sorry, parallel. All right, this is parallel to the field lines, the magnetic field lines. Okay, it's parallel. All right, so in a picture, if you see that, you know it's parallel. Okay, now what happens when it's parallel? Okay, so as the coil is turned from a vertical to a horizontal position like here, okay, what happens? Well, the magnetic flux, okay, first of all, decreases to 0. It decreases to 0, okay, because theta is now equal to 90 degrees. Okay. Simultaneously, okay, the rate of change, right, the rate of change of the magnetic flux, all right, in other words, this, with regards to Faraday's law, all right, increases when it is parallel to the field lines, okay, the rate of change. All right. Reason why though is because it reaches a maximum. All right. And the induced EMF and electric current. Last point here. Induced EMF and electric current. In the coil increases to a maximum. Right, so it'll be maximum output when it is the coil is parallel to the magnetic field lines. Okay, now the opposite will be true when the coil is vertical, right, or perpendicular to the field lines. Okay, the opposite will be true. Okay, so let's go have a look at that opposite quickly. Something just to mention quickly, alternating current is used in a generator, which is the right-hand rule, but the left-hand rule, which was not taught, of course, last year, that is a motor. All right, that's that's a motor effect, or that can be found in an electric motor. Alternating current is found in a generator, while direct current is found in a motor. And we haven't gotten there yet, so let's hope we can get there before the end of the session. But it's pretty easy because, yeah, it's just pretty easy, so don't worry about it. Okay, so that happens when the coil is parallel, but what happens when the coil is perpendicular? Right, let's just write that perpendicular a bit better. Perpendicular, we obviously know it's at a right angle, all right, to field lines. The opposite is true. Okay, I won't draw the coil. Obviously, perpendicular, it'll just be upright. It won't be flat like that. Okay. First of all, we know that the magnetic flux increases to a maximum. Okay, so it increases to maximum. The reason being is because now theta will be equal to 0 degrees. Other thing that happens is that the rate of change of the magnetic flux, okay, decreases to 0. Okay, it decreases to 0. And then, of course, the induced EMF, so induced EMF, okay, and the current, okay, would also decrease to 0. Okay, so that's what happens when they are, when the coil in the motor or in the between the magnets is at a vertical position. Now we're going to get to something that's called alternating current, AC, which is alternating current. That's what AC stands for, not aircon. Okay, alternating current generator. Right, generator, or sometimes called alternator. Alternator. Well, struggle to spell that for a second. Okay. Now, a generator, all right, that can generate alternating current will be known as an alternating current generator or alternator. Okay. Now, the most important component of this alternating current is called the two slip rings. Okay, two slip rings. Okay, and I'll show you all how that looks. Okay, now two slip rings, when you're looking at a diagram and you want to know is it AC or is it DC, how you identify it. Even if you have a textbook that has the electrodynamics section, I'll pull this up in an exam though, but I'll be able to tell you which one it is. Has you see two rings there, two whole rings, you know it's an alternating current generator. Okay, it's an alternating current generator. And how we would draw that graph, if we had a graph of alternating current, okay, now the best way to teach electrodynamics is just to have a look at the question. But you'll have a graph of alternating current, you'll have time on the x-axis, and then you'd have current, so I either on the y-axis or induced EMF. And alternating current would look like almost similar to a transverse wave in wave sounded light. Alternating current can go up as well as down. So if they give you a graph and they want to know is that alternating or is it DC or AC, you know it's AC because current goes positive and negative. With DC, direct current, a little bit different. Alright? If I show you how direct current works, okay? Now DC, alright, you can also get a DC generator. Okay, DC, which is obviously direct current. Direct current generator, which is called a DC generator. Alright, the reason how this works, the most important component here is the split ring commutator. Okay, split ring commutator will look in two dimensions, something like this. Okay, like that. Okay, very, very badly drawn. All right. And I'll have two ends on the one side here. Okay. But the most important part is that you'll see there is a split in the ring. All right. When you see that component, you know it's direct current. Okay. The two slip rings, all right, that would be replaced. The reason why we're able to notice that it's slip rings because there's two of them. The two slip rings for alternating current will be replaced by this component called the split ring commutator. Now, when you have a graph of DC current, okay, you got current here, or you got the induced EMF versus time in seconds, okay, and DC only populates or flows one way. In other words, it'll look like frog leaps. It's my colloquial way of explaining it. Like that. All on the one side. Okay? It's direct. Okay? It won't alternate from positive to negative like in the AC. It'll just go on top all the time. Alright. So, that is the difference. Okay. Quickest way to spot the difference between your two types of generators, split, AC or DC. If they don't give you a diagram of how the actual generator looks with the magnets and everything, and they give you the graphs, that's how you can denote it, which is direct and which is alternating. So in the question 9 of 2019 November paper, I had the privilege of, when I still taught for Rocklands High, to invigilate this paper. Alright, and of course, as a physics tutor, I could not obviously reveal that I was one, so I had to be extremely low-key walking around there. But I had a look at the questions and obviously saw, okay, cool, this is what's up. Okay, so, question 9, we start on a new page. But they say here, a simplified diagram of an electric generator is shown below. When the coil is rotated with a constant speed, EMF is induced in the coil. Now the first question there is this AC generator or a DC generator? Okay, now remember what I just taught you a few seconds ago. I taught that the way that you can obviously identify which is which is by looking for that one component. If we look for the rings, okay, remember this is not teaching, this is tutoring. Alright, if I look for the rings, do I see two of them or do I only see one? Answer me, guys. Are there two rings or is there one ring there? In the generator. A ring is circular. Do I see two or do I see one? One. Thank you, Zuleika. I see one. So, if I don't see two rings, or more specifically two slip rings, we'll look for a paper where there is a slip ring one. But if I don't see two slip rings, I know one thing is certain, it's not AC. What I'm looking at right now is a split ring commutator. Just below the coil, that circular object. I will hover my mouse over it in just a moment. That is a split ring commutator, and that's how a split ring commutator looks like. Alright, let me hover over here quickly. This component here. Okay, that's a split ring commutator. We won't go through any of the other questions too much. However, they say draw a sketch of a graph of the output voltage versus time for the generator. That's this graph. You just need to draw a vague one. Boom, boom. And they asked for the induced EMF, so you would need to write either, you'd actually need to write EMF in versus time. So that'll be EMF in brackets V for voltage, okay? And then boom. Okay, second question says briefly explain how an EMF is generated in the coil when the coil is rotated by referring to the principle of electromagnetic induction. Alright, that's explaining, of course, when the coil rotates. Okay, so basically you're saying when it rotates that the EMF is induced because there's a change in the magnetic flux that's linked with the coil. Alright, the rate of change in the magnetic flux. I don't even have to mention the rate of change, you can just say the rate of change. Okay, that's that. Alright, root mean square. This is a very important part of electrodynamics, as it's the calculation part of electrodynamics, okay? So, root mean square is the rate at which heat develops by an alternating current and direct current. We must know that that's obviously different. The potential difference that is produced by a DC source has the same energy dissipation meaning heating effect on resistance, as an AC source. Okay, if the DC potential difference is 1 over square root 2. So what we do is we call this the root mean square of voltage, or the root mean square of current. So what we'll have is we'll have something that's called Rms voltage, okay, which will basically be equal to 1 over square root 2 multiplied by the maximum voltage, right? So the formula will look like this. It will look like Vrms will equal to Vmax divided by square root 2. And then therefore you'll have current as well, which is the same, okay? The constant direct current will have the same energy dissipation as an alternating current, is 1 over square root 2 of the maximum alternating current. So the root mean square, Rms, will equal to Imax, or the maximum current, also divided by square root 2. So if in the question they ask you for, give the RMS voltage or the RMS current, you use either one of these two formula. And likewise, of course, if you know RMS values, you can just obviously find the maximum voltage or current values as well. Okay, the formal definition to formally define these two formulae. Okay, RMS value for an alternating current, Vrms, okay, is the direct, as they may ask you to define it, okay, is the direct current potential, the direct current potential difference or voltage that dissipates the same amount of energy as the AC, the alternating current. Now the same goes for IRMS. Okay, IRMS is the direct current that dissipates I think my hand feels like it's frozen. I'm struggling to write today. Dissipates the same amount of energy as the AC. Alright, there you go. So those are the two definitions of RMS values. Okay, RMS value for voltage and the RMS value for current. Now, believe it or not, we can apply the same to average power. Okay, and the formulae we find, if we just go to this exam quickly on the formula sheet down here, we'll see we have, where is it? Alternating current. So here we got the Vrms and IRMS, and here we got average power, which we know is equal to V times I. Okay, so how we do that, how these formulas are formed, all right, is if we take the concept of average power, which is P average, will obviously equal to the formula, or half times peak value of power. Peak value of power means P max, basically, I think. Okay, so equal to half times the maximum power. Okay, because the power of an AC source AC source, fluctuates between 0 and a maximum for each half AC cycle. Because power, if you look at the formula again, okay, is equal to V times I. Alright, V times I. Okay, so that means P max must equal to, so P average must equal to a half times, and P max must equal V max multiplied by I max. Okay, now we do have formulas for both of these, right? So we know that V max is equal to, and that's just a half of, because AC, remember, there's half cycles. So V max is equal to, let me just see what this is equal to. Let me just go back to this formula. Sorry, my brain is broken. IRMS. Oh, there we go. That's what I'm looking for. Okay, Vmax is going to equal to, of course, Vrms times 1 over square root 2. And this is going to be multiplied, of course, by IRMS multiplied by square root 2. Okay, that's what they are equal to. Alright, that's what they are equal to. So there we got Vrms, so we got a half times P average is equal to a half times all of that. Okay? Basically, we can form new formulae. Okay? We can form new formulae. Okay? So, since we're replacing everything here with square root 2, this is obviously a half, that's all going to be divided by 2. Okay? So what we have is new formulae to say, therefore, P average, okay, can equal Vrms multiplied by IRMS, okay, or another formula that we can have, of course, is to say P average, or the average power, can also equal to I squared RMS, so the RMS current squared multiplied by the resistance, or the average power can also equal to the RMS voltage, all squared divided by resistance. Okay, so basically the average power formula that we had in our formula sheet here, just under electric circuits, okay, we just replace I and V squared here, and up top here we just replace all those with RMS values, and boom bada ba, we sorted. Okay, that's all. Pretty cool. Okay, so that's how we can work out the average power of an AC generator, or of a DC generator as well. Alright, but just replacing everything here with RMS values. So for example, in the question above, question 9, 9.2, we had a 200 ohmic or ohm resistor is connected to a DC voltage supply as shown in diagram A. They told us the energy dissipates in 10 seconds and is 500 joules. The same resistor is connected to an AC source of 500 joules of energy, also dissipates in 10 seconds. And they want us to define RMS voltage. Okay, we gave the definition already. Alright, RMS voltage, the AC of an AC source, the AC potential difference, which dissipates the same amount of energy as a DC potential difference. Okay, and then of course they ask us to calculate the maximum peak voltage of the AC source. So maybe let's do this example. Okay, it's more than one method to do this, but let's maybe try and use it in the yeah, let me see, how can we do this to make this most okay, let's do this. Okay, so let's denote what we have. Let me maybe do that question. So the energy, which is in power terms, is obviously down to work, so we got 500 joules. We've got the time there, which was equal to about let's see, 10 seconds, and they asked us to calculate the maximum voltage. Now, in order to do that, we need the RMS voltage first. So we need Vmax equal to, but we also need Vrms as well. So we can in turn get that. We can use current if we want to. If you want to get the RMS current, I don't think it's necessary. Okay. So let's go to our formula sheet quickly. Let's pick a right formula, because we're looking for voltage. So let's look at circuits. What do we have? Okay, let's look here. So I'm going to use this one, right? W is equal to V squared times delta T over R, because also they told me the value for R was 200 ohms. So let's do this one. W first is equal to V squared times delta T all over R. So V squared, not sure what it is yet, but 500 was the value for W, times 10 over 200. Okay, so we can split that up, all right, to say, well, 500 will equal basically V squared over 1 multiplied by 10 divided by 200, and that basically is 1 over 20. So we end up with saying 500 is equal to V squared on top divided by 20, and you've got to multiply both sides by 20. Let's do that quickly. 500 times by 20, that is 10,000, and let's square root that answer one time, and we'll get V over here, which is equal to Vrms. Okay, this voltage is equal to Vrms, and it's equal to 100 volts. Okay, so if it's not maximum voltage, it's RMS voltage. Okay, now we can use the formula. V RMS is equal to Vmax divided by square root 2. So we've got 100 over here is equal to Vmax, which we don't know yet, divided by square root 2. Sorry, I have to crunch this up a little bit. And then on the side here, we can say, therefore, Vmax must be equal to 100 times square root 2. And we get an answer of 141.42 volts as the maximum voltage. Alright, now there's another method too. You of course could use any formula if you wish. I think there's about like 7 or 8 methods to do this. Alright, roughly about. But you'll still get all get to the same answer. This was relatively quick, of course. Relatively quick. So, yeah. Alright, let's have a look at the 2019 May-June. This is Adult Senior Certificate. Or Senior Certificate. They give us a diagram here. They say a diagram below shows the voltage output of a generator. And judging by this graph, we can already conclude that this is indeed a alternating current. Okay. And they asked, does this generator have split rings or slip rings? Now we know with a direct current, a generator, they make use of a split ring commutator, and an alternating current or AC generator makes use of slip rings. So our answer would be slip rings. 9.2, which one of the diagrams below, A or B, shows the position of the generator's coil at a time of 0,10 seconds? Over here. Well, we can definitely see that the potential difference there is 0. So the potential difference or induced EMF or induced potential difference there is equal to 0. And the only time that can happen is if the coil is perpendicular to the field lines. In this case, it would be diagram B. The rate of change of magnetic flux would also equal 0 in this case. So it's definitely diagram B. Sorry, not diagram 3. I was supposed to be 9.3. 9.3 says calculate the root mean square voltage for this generator. Okay, so looking here at the potential difference graph, this output number 312, either positive or negative, is the maximum voltage in this generator, produced in this generator. Okay, so if we find out what that is, let me find. We want to find out, sorry, the RMS voltage of the AC generator. Okay, obviously we know the formula for 9.3, we know the formula is Vrms is equal to Vmax divided by square root 2. So the Vmax though was 312, and we're going to divide that by square root 2. And the answer that we should get here for Vrms of the AC generator is, I think, 220, let me just check my calculator for this one again, 62 volts. Okay, off the 2 decimal places. Okay. Alright, that was a simple, straightforward one. Now we're going to go to 9.4.1. 9.4.1 asks for the average power. Because there is a resistance of 40 ohms, 40 ohm device, it's connected to the generator. Calculate the average power delivered by the generator to the device. Now we can do actually more than one method to accomplish this. Okay, we could use the simple formula, which is P average is equal to Vrms squared, or V squared RMS, or Vrms squared, whichever one you want to read that, divided by the generator. We've got the RMS value, so let's just take 220,62 and let's square it. And let's divide it by the resistance of the device, in this case, which was 40. If we do that, if we get that, we'll get that the average power will equal to 1216,83, and power is measured in watts, so that's 1216,83 watts as our average power. Now we could have done it another way. We could have decided to find the RMS current and then plug that in with the Vrms to get the average power. That would have been a little extra work. We could have also found out the maximum current and then just said Imax times Vmax divided by 2, and we'd have got a similar answer, just similar to this. However, less work to get the same output, still effective. It was only for 3 marks anyway, so we don't want to do more work that is required. Okay, so I would recommend just go straight to this formula, since we had the RMS value voltage, and we know straight off the formula sheet, average power is Vrms divided by resistance, which we were given. 9.4.2, the maximum current delivered by the generator to this device. Okay, now this is a nice question for 9.4.2. The reason why I say that is because we was already given, we calculated already the RMS voltage. We've also calculated the average power, and we also know the maximum. We also know the maximum current. Sorry, no, the maximum voltage. Okay, so we can go find a. Let's see if we can go do this. Let's go find a formula on the formula sheet quickly. Let's go see. Okay, so let's see. We've got P average, all right, and we got Vrms. Okay, we've also got P average is equal to I squared RMS times R, and we already know what that is, or because we want the maximum current. Alternatively, maximum current can also equal the Vmax divided by R. But let me see if I can try one of these formulae over here. Let's try PAV is equal to I squared RMS multiplied by R. So P average we got was 1216,83 is equal to I squared RMS multiplied by 40. So let's just divide both sides by 40 quickly. 1216.83. Let's divide that all by 40. And we'll get I squared RMS to equal 30, I'm going to write down the entire decimal 0.75 because we're going to square root it. And therefore we're going to get the RMS current to equal 5,5 515 or 52 amps. Okay, this is round off to 2 decimal places. Okay, now we know the RMS current, IRMS, is equal to Imax divided by square root 2. So we know that's going to equal 5,52 amps multiplied by square root 2 to give me the maximum current. And therefore Imax is equal to, let me just check this out quickly, 7,8 amps. Alright, so that's working from your power formula. Keep in mind, this was also, I think, 1, 2, 3, 4 marks, I think. Was it 4 marks? Let's check in the... Yeah, it was 4 marks, so it was a little bit of work. However, there also was a shorter method for it. Okay, now a shorter method would have been just recognizing that maximum current must equal to maximum voltage divided by R. Still applying Ohm's law here. Okay, if I want maximum current, I must work with maximum voltage. In this case, which was 312. The resistance was 40. 312 divided by 40 gives me also 7,8 amps. So we can still apply Ohm's law here, which is because remember we are working in relationship to electricity. Okay, the only difference is that we need to realize and recognize, of course, that if we want maximum current, we need to use maximum voltage to get maximum current. There's no maximum resistance, so that doesn't matter. If we want RMS, we need to work with RMS. Okay, so with power, this formula, I got the RMS current first, and then applied it into the IRMS equals Imax times square root 2. Safer method maybe, just to get it straight here, if you don't click that Ohm's law can also be used here. So maybe if you didn't think this far, it's fine. This is a simple method. All right, plug it in here, get the RMS current, plug it in here, get the maximum current. Same thing, 7,8 amps. Okay, doesn't really matter which one you choose, as long as you do it. Thank you so much, grade 12, for joining me on this tutoring lesson on electrodynamics. It was a great one. As you can see, it's mostly focused around the calculations. Very little theory, as you've seen in the past 2 questions. Alright, so lots of past papers will definitely prepare you enough for this section. Please don't forget to like and comment on this video, as well as subscribe to our channel, Good Better Best Online Videos, and we'll catch you in the next one.